In this video I'm going to run through why matter will take on different states. Recall from the previous video that we know that all matter is made up of particles and that there are forces between those particles, attractive forces. When we study this, we classify these two things according to these two basic kinds of bonding. There's intramolecular bonding. That means bonding inside of molecules. So if we have a water molecule, the polar covalent bond that exists between the oxygen and the hydrogen is an intramolecular force, as in within the molecule there's a bond there. But there are also intermolecular bonds. There are lots of different kinds of intermolecular forces, but just to give an example of one type of intermolecular force, I'm going to talk about polar covalent bonds. So if we look at the oxygen atom and the hydrogen atom that make up water, what we can see is that the oxygen atom likes electrons a little bit more than the hydrogen atom. What that means is, well, the oxygen atom isn't strong enough to rip those electrons away from the hydrogen completely. The shared electrons in this bond that I've shown here like to spend a little bit more time around the oxygen than they do around the hydrogen. What that means then is that oxygen, while it doesn't take on a full charge, takes on a little bit of a negative charge. We use this funny symbol here to put in front of that charge, but that symbol just means partial. So that's a partial negative charge that results from those electrons spending a little bit more time around the oxygen than they do around the hydrogen. Alternatively, these hydrogens, who don't get their fair share of those electrons, take on a partially positive charge. If we imagine another water molecule that exists some distance away, the partial negative charge associated with the oxygen atom will share an attraction to the partial positive charge on the hydrogen atom. This is called an intermolecular force. As it causes an attraction between different molecules. If you want an easy way to remember these things, think intra as in intramurals, those are sports that you play within your school, versus inter as in international relationships, which are like relationships between different countries. So intra means within, inter means between. This is called a polar covalent bond because now we have poles to the atom. So it's still covalent as it's a sharing, it's just an uneven sharing. These intermolecular forces lead to the different states of matter that we can observe. In a solid, the intermolecular forces are strong enough that despite the vibration of the molecules that occurs due to their motion, the molecules only vibrate back and forth about a fixed position. What that means then is that the intermolecular forces are strong enough to hold the individual molecules in place. This attraction is stronger than the inertia associated with the molecule's motion, and so this molecule can vibrate back and forth. Maybe it can vibrate this way and this way, back and forth and back and forth, but what it can't do is it can't fly away over here and get away from the other materials. What that means then, since the individual molecules are fixed in position, the overall material has a fixed shape and a fixed density. In a liquid, the intermolecular forces are strong enough to keep the molecules in a set area, but they are not strong enough to keep the fixed location of an individual molecule. What that means is if we have a glass of water, for example, all of those H2O particles are going to stick together in that liquid. None of them are going to pop out and go into the environment. But they won't necessarily fit in a nice regular crystal lattice like this. So they want to stay around each other and have their interaction, but they're not fixed in shape. So a liquid, as a result, has a fixed volume. All the molecules stay in the same general area. Alternatively, though, it does not have a fixed shape. The intermolecular forces are not able to keep those molecules in the location where they started. Finally, a gas occurs when the intermolecular force is not strong enough to keep the individual particles in the material at all, and so they fly off into the environment. As a result, the gas will spread out as much as the container will allow, and so we no longer have a fixed shape or a fixed volume, but we have a material that will fill its container. And now we can see the definition of the container for this gas is defined by the pressure exerted by the gas on the individual walls. So in something like a balloon, those gas molecules will spread out as much as they can push the container out, and then they fill the container. We do not have a fixed density. The density will depend on the size of the container holding the gas molecules. Why do different types of materials have different types of melting points and boiling points? Well, what we have to remember is that different materials are made up of different types of particles. The polar covalent bond that exists in a water molecule creating dipoles which create intermolecular forces does not necessarily exist in all types of molecules. For example, if we compare water and methane, or natural gas, we can see a couple different things that work to make the boiling point of water, or the melting point of water, much higher than what we see with methane. First, oxygen likes its electrons a lot more than hydrogen, and so we get that dipole, or we get that partial negative and partial positive charge created. Alternatively, while carbon likes electrons a little bit more than hydrogen, it doesn't like them enough to create those polar covalent bonds. So first of all, the carbon doesn't take the electrons from the hydrogen as much as the oxygen does. So we don't get any partial negative or partial positive. That's reason number one. So the carbon doesn't take electrons, shared electrons, as much. Maybe instead of take, I'll say it doesn't hog shared electrons as much as oxygen does. But the second reason why we have a very low melting and boiling point for methane is due to the shape of the overall molecule. Even if the carbon did try to hog those electrons a little bit more than hydrogen, what we can see is that the uneven sharing would go equally in each direction. Methane is symmetric, which means even if a little bit of charge did exist due to an uneven sharing, that uneven charge would go in all four directions evenly. You have to imagine that methane in a 3-dimension. I've drawn it in 2, but you have to imagine it in 3. And what that means then is that even if it was partially positive up, down, and to the left and to the right, that's all going to cancel out, and the overall molecule won't show that charge at all. So for 2 reasons, methane is going to have less intermolecular attraction between its individual molecules. Since that's the case, what that means is the methane particles won't want to stick together like the water particles do. And so at a lower temperature, the methane will become a gas. That's why we have states of matter and how it's related to the intermolecular forces between them.